All right. So this slide actually summarizes very well today what we've covered. So we're motivated by big data challenges. And I also noticed that there are many technologies relevant. We talk about Hadoop MapReduce in the morning, and also followed by HBase. And we just talked about pig-Laden. And this section, I'll talk about Twister. The understanding of MapReduce has been growing in people's activities. So in the context of MapReduce, we need to understand it's not just data processing runtime systems. If you put into the context of the whole system stack, like this chart shows, the MapReduce is just a very thin layer in the middle. When you talk about data processing, you have to talk about file systems, object stores, and all those kind of storage management. And we illustrate very well that in order to accelerate processing, make it a programmable interface more friendly, you need to integrate a high-level language support. And on top of that, even if you have the runtime, you might want to composite all this kind of a component with the other distributed functions. So you use services, workflow to define them. And why we can make it a distributed system? Because you can add another components like portal interface and the packages of security, provenance, and ultimately the goal is that provide software as a service, including a variety of algorithms, applications in science domain. To make the performance scaling, so we also need to take consideration of the hardware specification. So this will interface with the lower level infrastructure. For instance, that we give you a demo about how to use a virtual appliance, which is equivalent to a grid appliance today, and actually your testing environment is a VirtualBox. We also, tomorrow, we introduce how to run MapReduce on Azure cloud. You can run this kind of a MapReduce system actually on HPC cluster bare systems. So if you look at the MapReduce, and if you put it in the context of a distributed system, it's very rich. It basically has a lot of interface with different kind of a component of a whole systems. That's why that the research area of MapReduce is very booming, because people trying to address this problem at different angles, try to optimize support more applications. Twister is the iterative MapReduce framework, and this slide is prepared with the support from Bingjing Zhang as a PhD student at Indiana University. So what do I want to talk about? Mainly three areas. Why is the motivation? Why we use Twister iterative MapReduce? Basically, this defines the scope of our application we support, which typically is data mining and data analysis applications. Secondly, we want to ask is that, what is Twister? What is the architecture features? Thirdly, I will give some demos about how to use Twister to support data mining algorithms. I like this slide a lot. This is from Intel's application stack. It summarized very well of that in Intel's perspective, what will be the applications have impact in the future. So if you look at the top layer, you can see that computer vision, rendering, physical simulation, financial analysis, and the data mining are the areas that are very important for society and science. And look down one level, you can see a lot of kernel algorithms. For instance, support vector machine and the partial differential equation, natural language processing, and clustering and indexing. So these functions have all kernel functions you have to address in order to apply to those applications. And another layer pushed down, you can see that in order to make all these kind of algorithms running, you must support a layer of runtime systems. This including the iterative solvers. And going down another level is the classic basic matrix primitives, including sparse and dense or structured and unstructured. So this chart illustrates the importance that we need to make a very efficient kernel runtime system, including iterative solvers. because everybody can optimize their own applications. But the key is that what kind of abstraction is the kernel systems you have to address to be efficient and general. So that is the motivation why we study this kind of iterative MapReduce. And that's because the iterative algorithm is pervasive. Recall that almost 99% of the graphics algorithms are iterative. So I will cover in detail the examples of iterative applications. Traditional MapReduce, as we already studied, like Hadoop, they're very well for running for data parallel applications. We already show you example of a word count, and there could be other examples. But there are some issues because Hadoop kind of applications do well on data parallel applications, but they cannot support effectively for iterations. This has been illustrated by Disk.io. They actually optimize for fault tolerance, but on the other hand, it sacrifices the performance. Another extreme type is MPI. That is a classic HPC, cluster and supercomputer runtime system, very flexible on communication layer. But on the other hand, it's challenging to use it for two reasons. One is the fault tolerance support is natural. It's not natural because they use checkpointing. And secondly, the level of programming is a low level because you have to understand the communication point-to-point in a collective at a very low level. Basically, the users or the programmers has to understand the parallelisms. Because of these reasons, we're trying to summarize that what is the iterative MapReduce and how do we quantify the scope we want to research for. So we all know that MapReduce is a programming model, and the mainly is that to solve big data problem. They bring the computation to the data because data is too big. It's very difficult to move. On the other hand, we already said that data mining, data analysis are very important, even in the cloud, for processing simulation, for scientific data, for social media data. So we're trying to find a runtime system or programming model extension to address this class of problems. On top of that, people would like to ask questions like, is that iterative MapReduce can run on both HPC system or cloud? We need to answer that question. So if they could, the scientists would be able to address all their application problems, not worry about the lower level optimization. The other features we want to consider is reproducibility. It's very common that in science or engineering, we cite other colleagues' work by literature, by the papers. But often you really don't know how that data or result has been generated. It would be great that you're not only sharing their knowledge, but their data or the whole process of the software to reproduce that. So this is one of the goals that people trying to achieve. So actually, we have showed you that in the morning by Jonathan that how to build a VM, the software stack, so that you can reproduce in a way that to enable this.